In this video, I'm going to give a quick demo of this collab, which is Modern CNN Architectures Tutorials. Let's start with the first cell. We start by importing our deep learning tools from PyTorch and Torch Vision, making sure our environment is ready for heavy lifting. The output confirms PyTorch is loaded and a Tesla T4 GPU is ready with plenty of memory for training deep learning models. Next, here we build deep networks using different activation functions to clearly demonstrate the vanishing gradient problem. The output plot shows how sigmoid gradients completely die out after just a few layers, while ReLU maintains a strong gradients all the way through. Next, we implement the basic residual block, the fundamentals building block of early ResNet models like ResNet 18, ResNet 34. The text output shows the shape and parameter count of the block, highlighting how the skip connection preserves information. Next, we define the bottleneck residual block, which uses 1 cross 1 convolution to drastically reduce parameter in deeper models like ResNet 50. The output reveals a stunning difference. The bottleneck block uses only 6% of the parameter of a basic block, making deep networks highly efficient. Next, we put the blocks together to outline a complete ResNet architecture from the initial convolution layers down to the final classification stage. The printed table summarizes the entire ResNet family, showing how switching to bottleneck blocks allows ResNet 152 to stay relatively lightweight despite its depth. Next, we run a gradient flow simulation comparing a plain deep network against one built with our residual blocks. The output graphs visually proves the residual skip connection acts like a gradient highway, preventing the vanishing gradient problem entirely. Next, we implement the squeeze and excitation block, an attention mechanism that learns to focus on the most important feature channels. The output highlights that the SE block is extremely lightweight, adding less than 2% more parameters while significantly boosting model accuracy. Next, here we code the mobile inverted bottlenecks block, the highly efficient core of architecture like Mobile Net V2 and Efficient Net. The printed comparison shows that MB uses fewer parameters than standard convolution by leveraging depth-wise separated operations. Next, we outline the baseline architecture for coefficient net B0, which cleverly scales up depth, width, and resolution simultaneously. The output table illustrates this compound scaling method, showing how efficient net progresses from 80 to large variant. Instead of building from scratch, we load pre-trained efficient net models directly from Torch Vision, complete with ImageNet weights. The output, if we see, this output log shows the models downloading successfully, giving up instant access to word class feature extractors. Next, we define a flexible transfer learning function that can either freeze the pre-trained backbones or leave it open for fine tuning. The output confirms our setup. Freezing the backbone drops the trainable parameters down to just 5,000, while fine tuning trains all 11 million. Next, we set up our image transformations, making sure to use the exact ImageNet normalization statistics that our pre-trained model expect. The printed text emphasizes the golden rules of transfer learning, such as only applying data augmentation, data training. Next, we download the SIFAR10 dataset and apply our transfer learning transformers, realizing the tiny images up to the required 224 cross 224. The output shows the dataset downloading rapidly and confirms we have 5,000 training samples ready to go. Next, we implement a discriminative learning rate, a brilliant technique where we train the early layer slowly and the final layer quickly. The output table displays this in action, showing the learning rate decreasingly by a factor of 10 for each deeper layer in the network. Next, we define our complete training loop specifically tailored for transfer learning, handling the forward passes and back propagation. If we see the output, there is no visual output here. It just silently confirms that our training pipeline is successfully loaded into the memory. In the next code cell, we run a head to head comparison between three approaches: feature extraction, fine tuning, and training from scratch. The printed log shows the training progress over 5 epochs, with the fine tuning approach quickly pulling ahead in validation accuracy. Next, in the next cell, we visualize the results of our three-way comparison on a dual axis graph. The plot clearly shows the transfer learning converges much faster and achieves high accuracy than trying to train a model from scratch. At the last cell, finally, we print out a handy modern CNN cheat sheet containing the architectural structure of these advanced blocks. The text output gives you a quick text based references for building residual SE and MBCon blocks in our own projects. So that's it with this collab demo. Thank you.